Okay, let's continue. I'm sorry, in the last hour, I'm interrupted by the incoming phone. Okay, uh, so we can use the bisection method to solve uh, the roots of the characteristic equations. After we solve the Okay, after we solve the eigenvalues, then we can replace it okay. Then we can move it to the okay. Then we can solve the eigenvector from these equations. We can replace Okay, so we can replace the obtained eigenvalues into these equations. Then we can get a coefficient matrix, and the determinant of the coefficient matrix must be equal to 0. Okay, so that's the basis how we can solve the eigenvalues. So the determinant of the coefficient matrix for the x vector, it must be a singular matrix. Okay, since the requirement to solve the lambda values, we determined we need to get the determinant of the coefficient matrix must be equal to 0. Okay, but if the lambda I is a single, if the lambda I is a single root, then the rank of the okay. If the lambda I is a single root, then if we replace the lambda I into the coefficient matrix, then we can get a matrix. The rank of the matrix is equal to n minus 1. So if you do the Gaussian eliminations, usually we need to do the Gaussian elimination with the full pivoting. And then you will find the last row or the last equations, you will be all the coefficients, they are equal to zeros or very, very close to the zeros. Okay, so it means the number of independent equations will be n minus 1. Okay, so there is one degree of freedom for the solution vector space. That's the meaning of the rank of the coefficient matrix. But if the lambda I is a double root, then if we replace the lambda I into the coefficient matrix, you will find the rank of the coefficient matrix will be n minus 2, will be n minus 2. And the other, if the root is a triple root, then the rank of the a minus lambda IB, the rank will be the n minus 3. Okay, so if we got a double root, so that's why I said we can always find if there is a double root, we can always find two independent eigenvectors corresponding to these same eigenvalues. Okay, so if the A minus lambda I B matrix, the rank is n minus 2, then it means the dimension of the solution vector space is equal to the 2, is equal to 2. So we can find the two independent eigenvectors. The eigenvectors also, they are the solutions of these sets of the simultaneous equations. And after we solve the lambda I, there are infinite eigenvectors, or there must be infinite number of the solutions for these equations. Okay, so however, the number of the degrees of freedom or the dimension of the solution vector space depends on the character of the eigenvalue lambda I. If the lambda I is a single root, then we can find one independent eigenvector. And if the lambda I is a double root, then we can find two independent eigenvectors. Okay, for the same lambda I. Okay, so then you need to use the technique when we solve the solution vector space. How can we find the basis vector for the solution vector space? The technique to get the basis vector for the solution vector space, it is the same for us to find the basis vector for the eigenvectors for the corresponding eigenvalue lambda I. And the obtained eigenvector, sometimes we like to do the normalizations. Usually the normalization was taken about the matrix B. So we need to divide the obtained eigenvector by the values of the value should be 1 divided by the square root of the xi transpose bxi. So after we calculate this number, take a square root and the inverse now. Okay, so that's the technique. We can use the characteristic equations, and then we can solve the roots for the characteristic equations. And after we solve the characteristic equations, they are also the eigenvalues. And after we solve the eigenvalues, then we can replace the obtained eigenvalues into this matrix. And then we can solve the corresponding the eigenvectors. Okay. Then I will go to the next solution method for the eigenvalue problems. The characteristic equations, and usually they are used for the small dimensions of the matrix A and the matrix B. However, most of the time we are interested in a very large dimension of the matrix A and matrix B. Okay, let's consider the generalized eigenvalue problems. So we have both matrix A and matrix B on both sides of these equations. And the next solution method is called the vector iteration method. Which is called vector iteration method. Also, sometimes it is called the power method. or can we use the vector solution method to solve the eigenvalues and eigenvectors? And let me introduce the solution procedure. And I will introduce the solution procedure first. Then I will try to prove why the solution procedure can give you the eigenvalues and eigenvectors. The solution procedure first, we just assume an arbitrary initial vector. Let's say that's the V0. Okay. You just assign arbitrary values to each element in this vector. And let's assume the dimension for the A and the B matrix, they are the n by n matrix. And the dimension for the eigenvector x should be an n by 1 matrix. So they assume the vector also it needs to be an n by 1 vector. So there are n elements in this vector. You just assign arbitrary values to this vector. Sometimes you can use the random numbers. So you can generate random numbers, assign those generated random numbers into each element in the vector U0. And then we need to iterate from the initial vector, And there are two solution procedures. The first one is called the inverse iteration procedure. For the inverse iteration process, we can solve the U1, which is equal to A inverse B U0. Okay. After we assume the initial vector to be the U0, and for the problems, we know the coefficient matrix for both matrix A and the matrix B. Okay, but we like to solve the eigenvalues lambda and the eigenvector x vector. After we assume the initial vector U0, then we can calculate the A inverse B to be the U1. And also there is another iteration method which can be called the direct iteration method. If we use the direct iteration method, then the U1 will be the B inverse A U0. Okay, so we can use both procedures, either inverse iteration method or the direct iteration method, and it will lead you to the different eigenpairs. However, the obtained solutions they are always the eigenvalues and the eigenvectors. Okay, so most of the time we will choose to use the inverse iteration method. So the U1 will be the A inverse times B times U0. Okay, that's the most common solution procedure for the eigenvalue problems. Okay, then we will keep on going for the solution procedure. Uh, next cycle. So we will calculate the U2 is equal to A inverse B U1. Okay, after we got the U1 vector, the U1 vector is equal to the A inverse B times U0. After we got the U1, we just repeat the same procedure. We need to multiply the A inverse B to the U1 vector to get the U2 vector. And then we will keep on going. Okay, we will use the A inverse B times the obtained vector from the previous iterations. So if we got the UM vector, then how can we get the UM plus 1? We just multiply the A inverse B to the UM vector to get the UM plus 1, to get the UM plus 1. And how can we decide, how do we terminate the iterations? The termination for the solution procedure, if the is almost, or you can say it's very, very close, it's almost there. If the UM plus 1 is almost parallel to the UM vector, if the UM plus 1 is almost parallel to the UM vector, then it means that we can terminate the iterations. And if you don't do any modification for the obtained vectors, then you need to check whether the newly obtained vector UM plus 1 is almost parallel to the UM. So it means the almost equal to alpha times. Okay, so it means all these elements in the UM vector and the UM plus 1 vector, they can be obtained by multiplying the same constant alpha. If the ratios of the same elements, the same number of the elements in the UM plus 1 and the UM, the ratio is close to a constant, then we can say these two vectors, they are parallel to each other. Then it means you can stop the solution procedure. And for some programs, they like to do the normalization. If we do the normalization in each iteration, so the UI is equal to okay. In each iterations, if we divide the obtained UI vector by a scalar, the scalar is calculated from the UI transpose BUI and take a square root. If the UI vector divided by this one, we get a new vector. The U bar vector is parallel to the UI vector, but we need to do the normalization for this one. If we do the normalization in each iterations, then the check of the convergence then you don't need to check whether these two vectors they are parallel to each other. If we finish the normalization in each iteration, then you can check the U bar n plus 1 is almost the same as the U bar n. Okay, then the iterated vector, the newly obtained vector from the iterations will be same as the obtained U bar vector from the previous iterations. If these two vectors they are almost the same, then you can terminate the iterations, so you can get the approximate solution for the eigenvector. You can get the approximate solution for the eigenvector. Okay, I will take a break here, and today you will have the 4. Probably I will give you 5 parts.